Crystal Physics Part 2. Crystal Systems. All the non-crystals are classified into 7 types of crystal systems. This is based on the relationship between the lattice parameters of a crystal. Here in 3 dimensions, there are certain basic crystal systems. First one is cubic. In this, the sides A, B, C both are same. A equal to B equal to C and alpha equal to beta equal to gamma equal to 90 degree. That is the angle between two sides, that is equal to 90 degree. See, a cubic crystal is shown. The dots represents lattice points. Second one is tetragonal, that is a crystal system. In that, A equal to B, two sides are equal, but third side is not equal. Again here, the angle between all the angles, alpha equal to beta equal to gamma equal to 90 degree. The figure of a tetragonal is also shown here. Third type of crystal system is orthorhombic. That is, here the sides are not equal. A not equal to B not equal to C. All sides have different lengths, but the angle alpha, beta, gamma are same. That is equal to 90 degree. The figure of an orthorhombic is also shown. Here also the points represents lattice points. Fourth one is hexagonal. See, in this case, two sides are equal. A equal to B. But the third side is not equal. A equal to B not equal to C. The two angles alpha beta equal to 90 degree, but the third angle gamma is about 120 degree. Then next type of crystal system is monoclinic. In this, here also the sides are not equal. A not equal to B not equal to C. The angle alpha and gamma here is equal to 90 degree, but beta that is not equal to 120 degree. But beta is equal to 120 degree in the previous case, hexagonal, gamma equal to 120. Here alpha gamma equal to 90 and beta not equal to 120 degree. Then triclinic, here A not equal to B not equal to C and alpha beta gamma not equal to 90 degree. Alpha not equal to beta not equal to gamma not equal to 90 degree. See, all are different. All angles and all lengths are different. Such a crystal system is triclinic. Now one more, trigonal. Here A equal to B equal to C. All sides are equal, but alpha equal to beta equal to gamma not equal to 90 degree. All sides are equal, all angles are equal, but not equal to 90 degree. That is the situation corresponding to trigonal crystal systems. These are the 7 basic crystal systems. See, in this table, the basic crystal systems are given. Their lengths proportionality and angle proportionality is also given. Examples are also given. Here for cubic we can take crystals like gold, copper, sodium chloride, etc. For tetragonal, titanium dioxide, SnO2, NaSO4, etc. Orthorhombic, KNO2, BaSO4, barium sulfate, lead carbonate, etc. Now monoclinic, here it is CaSO4, 2H2O gypsum, FeSO4, etc. Now triclinic, K2Cr2O7, CaSO4, 5H2O, etc. Trigonal, arsenic, antimony, bismuth, etc. For hexagonal, examples are SiO2, zinc, magnesium, etc. Next, lattice centerings. The different possible arrangements of lattice points in a crystal are 4 types mainly. First one is primitive. Here the lattice points are arranged at the corners of the figure. Okay. Next one is body centered. Here lattice points are arranged at the corners as well as inside the body. There is one lattice point inside the body. In these lattice points, here atoms or bases are attached that can convert it into crystal systems. Another one is face-centered FCC. Here you can see lattice points at the corners as well as at the face centers. Another one is C-centered. Here you can see for a cube, atoms or lattice points are attached at the corners as well as two opposite sides, two opposite faces. Okay, that is we can have three pair of opposite faces for a cube, so that there is no peculiarity in where the lattice points are located. So it can be A-centered, B-centered or C-centered. That depending upon the faces, the pair of faces, opposite pair of faces where the lattice points are located. So these are the four types of lattice centering. Lattice centering means the different possible arrangement of lattice points in a crystal. So we have Bravais lattices in 3 dimensions. That is a combination of the 7 type of unit cells or basic crystal systems plus these 4 types of lattice centrings. That results in 14 types of Bravais space lattices in 3 dimensions. See, in this picture you can see in one of the basic crystal system cube, it has 3 possible different lattice centerings are possible. See, primitive, body centered and face centered. Both are possible. In tetragonal type, 2 types of lattice centerings are possible. P stands for primitive and also I for body centered. For orthorhombic, all the 4 types of lattice centerings are possible. See, primitive, body centered, face centered and C centered. In hexagonal, only primitive type lattice centering is possible. In monoclinic, primitive and C centered, or it can be B centered or C centered depending upon the pair of faces where it contains lattice points other than corners. Then for triclinic type of crystal system, primitive, only primitive types of lattice centering is possible. For trigonal, also primitive is possible. See, in this table you can see the 7 basic type of crystal system and number of lattice that are possible and also their symbol and the relation between lattice parameters is also shown here. Now, crystal symmetry. Patterned self-similarity, that is what meant by symmetry. The definite ordered arrangement of faces and edges of a crystal is known as crystal symmetry. Symmetry, that's a powerful tool for the study of internal structure of crystals. Crystals possesses different symmetries or symmetry elements. Symmetry, that is based on symmetry operations. Symmetry operations, when performed in a crystal, that leaves the crystal invariant. Symmetric groups, that are group of all isometries of an object which is invariant with respect to symmetry operations. Symmetry operations can be performed about a point or a line and are called point group symmetry operations. That can also be performed by translations that are called space group symmetry operations. Crystals exhibit both types of symmetries independently and in compatible combinations also. After performing an operation on a body, if a body becomes indistinguishable from its initial configuration, the body is said to possess a symmetry element corresponding to that particular operation. The different point group symmetry elements exhibited by a crystal are center of symmetry, reflection symmetry, and rotation symmetry. First one, center of symmetry, also known as inversion center. It is the center of symmetry exists in a crystal if an imaginary line can be extended from any point on its surface through its center, and a similar point is presented along the line equidistant from the center. See, here the first two pictures represents a two-dimensional and the third one represents a three-dimensional. Here for a circle, we can have its center that satisfies the condition for center of symmetry. Here in the last picture, the center of cube is one from where we can draw lines that are line. If we draw a line to one side, we can see another point equidistant from the center opposite to it. That represents center of symmetry or inversion center. 2 is reflection symmetry. Reflection symmetry, also known as mirror symmetry, that is symmetry with respect to reflection. A figure that which does not change upon undergoing a reflection has reflection symmetry. The reflected shape will be exactly the same as that of original, the same distance from the mirror line and the same size. See in the picture, left hand, after showing in mirror, left and right looks same, so we can say it possesses reflection symmetry. In the second picture shows a molecule on reflection, left and right hands reflection. After reflection also it looks same. In last picture also the planes are shown, that gives us reflection symmetry. Third one is rotation symmetry. Rotational symmetry is the property shape when it looks the same after some rotation by partial turn. See, that is, the degree of rotational symmetry of an object is number of distinct operations in which it looks exactly the same for each rotation. We can rotate an object about a particular axis at a particular angle. If it looks same before and after rotation, we can say that possesses rotation symmetry. In that picture, in the first picture, there is an axis is shown. So after a rotation through a particular angle, it looks same. Before and after rotation, the molecule looks same. See, that's also shown in the second picture. There is an axis. We can perform rotation. Say in that second picture, we can rotate it about 90 degrees so that it looks same if after and before rotation. So we can say it possesses rotation symmetry with respect to that axis.